Theorem: if the roots of lemda1 lemda2 of the characteristics equation lambda square minus a plus d into lambda plus ad minus bc equals to 0 are unequal real and of the opposite signs, then prove that the critical point 0 of the linear autonomous system dx over dt equals to ax plus by, dy over dt equals to cx plus dy. Equation 1 is a saddle point. Now proof: without any loss of the generality, we may assume that lemda1 is less than 0 is less than lemda2, since from the theory of the linear autonomous system we know that the general solution of equation 1 is given by x equals to c1 a1 e raised to power lambda 1 t plus c2 a2 e raised to power lambda 2 t, y equals to c1 b1 e raised to power lambda 1 t plus c2 b2 e raised to power lambda 2 t. Equation 2, where a1 b1 and a2 b2 are the definite constants, with a1 b2 minus a2 b1 not equals to 0, and c1 and c2 are the arbitrary constants. Now for c1 not equals to 0 and c2 equals to 0, we get the solutions: x equals to c1 a1 e raised to power lambda 1 t, y equals to c1 b1 e raised to power lambda 1 t. Equation 3, and for c1 equals to 0 and c2 not equals to 0, we get the solutions: x equals to c2 a2 e raised to power lambda 2 t, y equals to c2 b2 e raised to power lambda 2 t. Equation 4, for c1 is greater than 0, the solution of the 3 represents a path consisting of the half line b1x equals to a1y. For any c1 less than 0, they again represents a path consisting of the other half of the line. Further, since lambda1 equals to 0, both lambda1 is less than 0, both of these half lines paths still approach and enter 0 as t tends to infinity. On the other hand, for c2 greater than 0, the solution of the 4 represents a path which consists of the half of the line b2x equals to a2y, while for c2 is less than 0, they again represents a path consisting of the other half of the line. But since lambda 2 is greater than 0, therefore both of these half line paths now approach and enter 0 as t tends to minus infinity. If c1 not equals to 0 and c2 not equals to 0, the general solution of the given by equation 2 again represents a non-linear paths. But since lambda 1 is less than 0 is less than lambda 2, it follows from the equation 2 that none of these paths can approach to 0 as t tends to infinity or t tends to minus infinity. Further, none of these paths can pass through point 0 for any t0 such that minus infinity is less than t0 is less than infinity. The general solution of the given equation 2 clearly shows that each of these non-rectilinear paths correspond to c1 not equals to 0 and c2 not equal to 0 becomes asymptotic to one of the half line paths defined by solution of the given equation 3 and t tends to minus infinity and equation 4 as t tends to infinity. Thus there are the two half line paths which will approach and enter point 0 0 as t tends to infinity, and other half line paths which approach and enter point 0 0 as t tends to minus infinity, and all the other remaining paths which are non-rectilinear and the which neither approach 0 0 as t tends to infinity or t tends to minus infinity nor pass through the point 0 0 for any of t0 such that point minus infinity to t0 is less than t0 is less than infinity becomes asymptotic to one another if the four of the lines paths as t tends to infinity and t tends to minus infinity. Hence the critical point 0 0 is a saddle point which is unstable.